this, we are essentially ready to go. The rooms which we have will be Turlington L005 and Turlington L011. Now, I neglected to do one bit of bookkeeping, and that is, prior to this rescheduling of exam 1, I had a room which was large enough for all of you folks. I had this room. But I didn't want exam 1 last week, Wednesday. That was not the right time. So what I still have to do is to decide how many of you go to Turlington L005. I'll start with the letter A, alphabet. Take the list of you, divide by 2. But I don't know where the division by 2 comes. Is it after the letter M? After the letter N? I don't know. I forgot to take a look. Big deal. So I'll take a look at that this afternoon, post it to Sakai, and of course announce such on Wednesday. Now, if you have a legitimate conflict with Thursday evening, the time of the exam, my request is that you take the exam earlier in the day, in the time slot 2 to 4 p.m. or the time slot 4 to 6 p.m. in Lee 309. Very nice location. It's the department conference room. For those of you who need to do this, who are in the early bird category, I need from you a note just to let me know that I will expect to see you earlier in the day on Thursday and make accommodations accordingly. So if you're in this conflict category, give me the note. If you can't make the scheduled exam, and you can't live with this early bird arrangement, then you need to see me individually in my office. Everybody understand this? No big deal. All right, let's proceed with.
Is there any chance of getting extra time, so it's like 10 to 10:30?
My plan will be, shh, don't tell anybody. I'll let you work till 11 p.m. I'm not of a mind to put time pressure on you. Why the university has decided, because they actually say 8:20 to 10:10 p.m. That's not enough time. And I don't want their bad decisions to affect educational progress, period. So, let me go back to this early bird thing, because I really have the room starting at 1 p.m. So I'll put down here, or start at 1 p.m. So if you can start at 1 p.m., 2 p.m., or 4 p.m. for early bird, tell me. But don't pick 1:30 or 2:45 or I can't be making all kind of different schedules and go goofy back and running back and forth to Lee 309. Okay, fair enough? And with this, I'll let you work at least 2.5 hours. I want to see how much you've learned. I don't want to squeeze you for time. I don't think that's a good idea at all. I don't like it. Shh, don't tell anybody. All right, back to buffers. Question 1838 we did last time. 100 mils of 0.80 molar ammonia combined with 100 mils of 1.0 molar ammonium chloride solution, to which 0.020 moles of HCl are to be considered added. After which, your duty assignment is to calculate solution pH, or hydronium ion concentration, same thing. Now then, just to show you how buffers operate, the pH of this system before you add the HCl is 9.15. So the hydronium ion concentration is pretty close to 1 times 10 to minus 9. Then we add the HCl, 0.020 moles thereof. The pH reduces to 8.95, not much of a change in pH. Now notice, this system volume is 200 milliliters. If you have 200 milliliters of deionized water, or regardless of the volume, if you have deionized water under normal lab conditions, what's pH? 7.00 to 2 sig figs, okay? We know this. If I added the 0.020 moles of HCl to 200 milliliters of deionized water, given that the original pH of the deionized water is 7.00, what kind of pH am I going to wind up with for the resulting solution? Put another way, is water by itself a buffer? Hell no. Well, with this consideration, you'll see why. 200 milliliters, deionized water, pH 7.00. Now we add 0.020 moles of HCl. And all the HCl we add converts to what? Hydronium ion. So we'll have 0.020 moles of hydronium ion contained in 0.20 liters of solution volume, right? What's the molarity? .020 moles hydronium ion in 0.20 liters of solution. What's the molarity? 0.10. What's the pH? 1.00. That pH changed from pH 7.00 to pH 1.00, corresponding to a millionfold change in the hydronium ion concentration. Here's 200 milliliters of a different solution. We added the same amount of HCl. Did hydronium ion concentration change a millionfold? Hell, it didn't even change tenfold. See how a buffer operates? All right, back to 1839. 1839 takes off from 1838. It says, let's go back to 1838 after this part of the puzzle and add some more HCl gas until the resulting solution from 1838 has its hydronium ion molarity quadrupled, multiplied by 4. Nothing fancy about this. Well, there's the hydronium ion concentration for this pH, for the 1838 solution after the HCl was added. I reported it to 3 sig figs because we'll change it to 2 sig figs after we do our arithmetic. Well, I multiply that by 4, I get 4.48. Here is the Ka expression I'm going to use to get a handle on pH. Here's the hydronium ion concentration. Following from 1838, after the HCl was added in 1838. Recall, if you will, the resulting molarity of ammonia was 0.60. And the resulting molarity doesn't look right. Let me take a look. Something looks wrong. Aha. That's more like it. Never mind molarity. The resulting moles of ammonia was 0.060, and resulting moles of ammonium ion was 0.12. And recall, we are at liberty to use moles in this expression rather than convert the concentration, because converting the concentration would involve dividing this term by the solution volume and this term by the same solution volume. Unnecessary arithmetic. So the heck with that. And just like in 1838 for 1839, when we added the HCl, what did we do? We killed more ammonia and made more ammonium ion. So if X represents the moles, additional moles of HCl added, to bring about a quadrupling of the hydronium ion concentration, then X will also be moles of ammonium ion made and moles of ammonia killed. So, if we started with 0.060 moles of ammonia following from here, here's how many moles of ammonia we'll have after we added this additional quantity of HCl. Here's how many moles of ammonium ion we'll have after we added this additional quantity of HCl. Well, that's a big deal. One equation, one unknown. And when you see this Ka value and this hydronium ion concentration, I hope you immediately do this to make arithmetic a lot more simple. You get 0.040 moles of HCl to be added. All right, let's go to 1840. A very similar problem. 1840. Imagine that we are given 100 mils of 10th molar to 2 sig figs acetic acid solution. I'm going to treat this with sodium hydroxide solution at a molarity of 0.10 to produce a solution which has a pH of 5.00. Did you do something like this in lab? Have you done something like this in 46L? Which assignment? 46L, which assignment? Assignment 1, the first assignment you did. Now, we didn't ask you to do any arithmetic on that first assignment, but you did monitor pH change as you added. This is back to assignment 1, the last part of assignment 1 in laboratory. In one case, you took some acetic acid solution and treated with HCl solution. In the second case, you took acetic acid solution and treated with sodium hydroxide solution. Remember doing that? Which of those treatments resulted in the production of a buffer? Both? Neither? Acetic acid solution. Case 1, treated with HCl solution. Case 2, treated with sodium hydroxide solution. Which treatment makes a buffer? Case 2. Treating with in order to have a buffer, starting with acetic acid solution, I've got to create, beside acetic acid, a high concentration of what? What? What's the conjugate base of acetic acid? Acetate ion, isn't it? Am I going to produce acetate ion from acetic acid by treating acetic acid with hydronium ion? Because that's what I do when I treat it with HCl solution. Do I deprotonate acetic acid molecules by treating them with hydronium ions? Yes or no? Hydronium ion, stronger acid than acetic acid. Acid react with acid to make a base? Come on now. This is utterly absurd. Think about the chemistry first and foremost. But if I add hydroxide ion to acetic acid, then I'm going to pull H plus from acetic acid molecules. And in so doing, I create acetate ions. So the treatment with sodium hydroxide solution, or hydroxide ion itself, makes a buffer, doesn't it? Will this treatment make a buffer? You're damn right, because it's the same thing which we just talked about. That you did at the tail end of assignment 1 in the lab. So I'll write Ka for acetic acid. Then I'm going to take this Ka expression and rearrange it ever so slightly. I'm going to take the hydronium ion molarity and put it over here. That's all I did. In order to recognize, okay, that I'll now have Ka divided by hydronium ion molarity. Ka is 1.8 times 10 to minus 5. At pH 5.00, the hydronium ion molarity is 1.0 times 10 to minus 5. And that's equal to the acetate ion molarity divided by the acetic acid molarity, or a ratio of the acetate ion concentration to the acetic acid concentration, which is 1.8 to 1. Okay? So I'm going to make a solution in which the molarities of each of these ions is appreciable. So I will be making a buffer. Now then, here's the chemistry. Acetic acid, treated with hydroxide ion, converts to acetate ion and water, extent quite large. Now then, in my 100 mils of 10th molar acetic acid to 2 sig figs, I've got 0.010 moles of acetic acid. The addition of hydroxide ion in a quantity identified as X will give me an equilibrium quantity of acetic acid of 0.010 moles minus X. This is the amount of hydroxide ion I added. I put quotes on this because the hydroxide ion itself is not part of the arithmetic that we're going to do. X represents moles of acetate ion made. It represents moles of acetic acid killed. And of course also represents moles of hydroxide ion added. Okay? Now then, X, moles of hydroxide ion added. Moles of acetate ion made. How do we relate X to moles of acetic acid in this solution at equilibrium? We've got what we need to do, just that, on the board, because that will allow us to solve for X. X equals, in the part on the right is a relationship of X, which is moles of hydroxide ion added, same as moles of acetate ion made. And we want to relate this to moles of acetic acid in the solution at equilibrium. Well, how many moles of acetic acid will we have at equilibrium? Here it is. Okay? But what will be the ratio of X to these moles of acetic acid? 1.8, isn't it? There it is. Follows from what we have right there. Okay? Solve it for X. No big deal. I get .018 moles. Now then, remember that the source of hydroxide ion in this system is our 10th molar sodium hydroxide solution. So the question, as it is stated in the notes, says, what volume of the sodium hydroxide solution? Wait a minute, this isn't right. That's right. I looked at the wrong data point. Pardon me. This is moles of hydroxide ion which we have to supply. So the question then is, what volume of this solution must be added in order to contribute this many moles of hydroxide ion? What volume of the sodium hydroxide solution has to be added to contribute this many moles of hydroxide ion to the system? I ask this question even though it's something you did or were supposed to have done in 2045, because many of you seem to be hung on stuff like this. What volume of this solution has to be added to contain that many moles of hydroxide? You follow the question? What volume of that solution has to be added? So I'm going to write 1.0 liters NaOH solution over 0.10 moles hydroxide ion. You agree with this? That's just the inverted molarity. Why did I invert the molarity? Am I not asked to calculate a volume? There's volume in the numerator. If I write molarity, it's liters in the denominator. That's per volume. I want to get a volume. And how many moles of hydroxide ion? That's it. 64 milliliters added in. All right? 1841. To get started with 1841, please take a peek back at 1822. Question 1822. When you take this back peek, you'll see that 1822 is the question where you are asked to consider mixing 200 mLs of 0.050 molar HCl solution with 100 mLs of 0.10 molar sodium sulfide solution. And after you make that mix, calculate the pH. Remember that problem? Wasn't too long ago when we tackled it. And what was the ticklish aspect of this calculation? The ticklish aspect was to realize in making this 200 mil, 100 mil mix of the HCl and sodium sulfide solutions respectively, you put together equal mole quantities of hydronium ion and hydroxide ion. So careless students in the past have reported, okay, the solution has a pH of 7.00. Wrong. Because there's one handle you must always have in your hands when you deal with any of these problems. At all times, always. What is that handle? What's the handle you always have to have on these systems in order to be able to analyze them correctly? What's the handle? PSI, period. If you don't know what's in the system, you can never understand its chemistry. So you always have to maintain your focus on what the heck's in the system. And if you take a system and treat it with something, then after the reaction which occurs, if a reaction occurred, after you treated the system with the something, then you write the PSI again. Always keep on top of system inventory. Without that, you lose. With that, you can always win. And we want you to win. I'm telling you what you have to do. So we wound up recognizing that after the equal moles of hydronium ion and hydroxide ion killed each other, we still had HS minus in this system as a species. And the acid-base table tells us that HS minus behaves as a base which is stronger than water. Also behaves as an acid, but an acid weaker than water. So we know that this system is basic. And we found that its pH was, I don't remember. The answer is in the notes. But the reason why that system was basic is because of the presence of HS minus after this mix was made. So what are we doing to this system? We're going to recreate this system and add an additional 100 mils of HCl solution. That's all. Okay? So, after adding the additional 100 mils of HCl solution, which means 300 mils of HCl solution total, okay, so I wrote this plus this. Okay. You will now have created a system in which initially you've combined 0.015 moles of hydronium ion and 0.015 moles of chloride ion. Who gives a damn? Because this is a base weaker than water, but it's there. And of course water itself. And 0.010 moles of hydroxide and 0.01 moles of HS minus, just like before. Okay? What happens? Well, we've got the inventory. After we've got the inventory, if we're looking for acid-base chemistry, we look at the inventory and pick out the strongest acid. We look at the inventory and pick out the strongest base. And we write the reaction equation. And we pay attention to extent. And we recognize that K for this is 1 over KW. So K for this is 10 to the 14th. A mere 100 trillion. So I'll take that as 100%, practically speaking. And realize that in this case, the 0.010 moles of hydroxide ion had what happened to it? What happened to the 0.010 moles of hydroxide ion? All got murdered, didn't it? Killed, wiped out, eliminated. Now, keep in mind that it's very fortunate that in chemistry class when we kill these things, if we want them, we can remake them. But for the system as it stands, we killed the hydroxide ion. And how much hydronium ion was killed? 0.010 moles. So how much hydronium ion remains after the hydroxide ion was killed? 0.0050 moles. Is there something else in this pot with which hydronium ion can react effectively? We look at the PSI and find out that yes, hydronium ion also reacts effectively with what?
HS minus.
Hydrogen sulfide ion, you betcha. What can you tell me about the extent of this reaction? Quite large. Ka of this is only 1.1 times 10 to minus 7. Ka of this is 55.3. Is it fair to say hydronium ion is a good deal stronger acid than H2S? Absolutely. It's about 100 million times stronger, actually a little bit more than that. So I'd say stronger is okay. And large extent is certainly okay. And now after we've done this, to get at system pH, what must we do? I just told you. PSI, damn it. QPSI. If you keep a handle on the system content, you can understand its chemistry. And if you don't have that handle, you got nothing except confusion. And we don't want you to be confused. I don't want to have to continue to jump up and down and holler, but I will. It's just my way. Now then, we of course have been paying attention to PSI from this standpoint. Because whenever you have to do a calculation, the quantitative aspect of PSI is always part of the puzzle. So at this point, without writing it down, can you tell me how much hydronium ion remains? Practically zero. How much HS minus remains? How much H2S is present? Moles, of course. Does this look like a system for which calculation of pH is going to be difficult? What kind of a system does it now look like? Does it look like a buffer? Is a system with both H2S and HS minus, the conjugate base of H2S, present in reasonably high molarity? Goody. So tell me now, what piece of information from our acid-base table will we use to proceed with the pH calculation? 4? How about that? Let me look at the table and see 1.1 times 10 to the minus 7. I told you I see this table in my head. Don't worry about it. Your job is not to memorize this stuff. I tell my 2045 people, what the hell are you making these people memorize formulas for? What good is that? If they use it enough, they will memorize it. It's not part of learning. Learning is understanding. They are making you memorize formulas for tests, don't they? 2045? There's the chemical version of the equilibrium constant. Tell me the hydronium ion concentration right now for this solution. Tell me the hydronium ion concentration right now for this solution. Absolutely. Did we not make a solution in which these molarities are equal? So there's the hydronium ion concentration. Let this stuff talk to you. All right? Hey, we keep a handle on QPSI. We know these molarities are equal because you got equal moles of them. And they're both swimming around in the same solution, so the molarities have got to be equal. Done. Okay. Now then, 1842. (1842) is a calculation that's really not on a buffer solution, but it parallels buffer solution analysis. Because as you shall see for question 1842, which we shall now tackle, x squared over m sub I minus x does not apply, just like for any buffer. Okay? Here's what we're starting with. Deionized water. You've seen this before. Plus 5 drops of 0.50 molar HCl solution, which means 5 drops of a solution which is containing hydronium ion, chloride ion, and water. All right? The drop aqueous liquid has about what volume? You remember doing that determination in 2045L? Assignment 1? Woo! That's real ancient history. I mean, that's on the order of 4 months ago. Can't possibly hold me responsible for remembering something I did 4 months ago. The hell I can't and will. You ought to know that about me by now. I even do this stuff because it's important. I've already reminded you. 46L, many times this term. You're going to need small quantities of solutions. Half a milliliter. You know, fool around with that 10 ml graduated cylinder? I told you this before. Clean it, rinse, add, fool around, hydrophilic. I can't get all the solution out. What a pain. Get out a clean dropper. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 drops. Boom, you got it. There's your half mil. Done. That's what this is good for. Okay? Now then, from the 5 drops of this solution, at this volume for each drop, you can figure out how many moles of hydronium ion you're adding to the deionized water. And with that, you do this arithmetic. I'm not doing this arithmetic for you. You'll find out that, oops. The hydronium ion molarity becomes 0.024 in the 5 mils of deionized water to which this quantity of a half molar HCl solution has been added. You do that. Here comes the fun part. .0 milliliters, but this time .53 molar acetic acid. Now, as we do the arithmetic, you'll see why I selected this somewhat unusual molarity for the acetic acid solution. Plus 5 drops, D for drop. Do you recognize then the amount of hydronium ion we added to the deionized water is the same as the amount of hydronium ion we're adding to this acetic acid solution. Fair enough? Nothing fancy about that. But what do you think is the consequence of this m sub I value for the acetic acid solution after treating it with 5 drops of aqueous liquid? What is the impact on the m sub I value for the acetic acid solution of adding to it 5 drops of aqueous liquid? What's the impact on the initial molarity of the acetic acid solution? Is the initial molarity going to stay the same? Is the initial molarity of the acetic acid solution going to stay the same? Yes or no? No, why not? What are we doing to this acetic acid solution? If no reaction occurs, what are we doing at the minimum? Diluting it, aren't we? Ha ha! And now we got 0.50 molar acetic acid. That's m sub I. Okay? Here's the $64 question. Or let's state it as a directive. Show that H3O plus equals 0.024 for this system. Chemistry. This equilibrium alive and well in the acetic acid solution? You're daggone right. Question. What is the impact on this equilibrium as a consequence of adding this HCl solution? Is the equilibrium disrupted by adding this HCl solution? And on the disruption, what does this system do to get back to equilibrium? Does it do this, or does it do this? Right to left? Because we added this, guess what? You will find out, if you do the calculation correctly, that the quantity of hydronium ion added to this equilibrium system from the HCl solution stops the ionization of acetic acid to the extent that it does not contribute to the solution hydronium ion concentration. That's why it's 0.024, just like the DIW treated with this HCl solution. You got that directive? You're going to pick it up from this point tomorrow in discussion class. You better be there.